Okay, so good afternoon, everyone. So let's start the webinar today. So it's our great pleasure to invite Professor Ulrich Nierste from KIT, Germany, to give a lecture for us. And he received his PhD degree in physics from Technical University of Munich, Germany in 1995. He has been on postdoc positions in TUM, DAISY in Germany, and Fermilab in USA. And he was a CERN fellow during the 2000 to 2001, and an associated scientist at Fermilab during 2002 to 2005. And finally, he becomes a tenure scientist at Fermilab and full professor at KIT. His main field is quark flavor physics within and beyond the Standard Model, and he has many excellent works in this field. The talk title today is Heavy Quark Decays, Get to New Physics. So let's welcome our speaker. Yeah, please start.
Okay, yeah, I'd say good morning, but it's good afternoon for you. So thank you very much for this nice opportunity. And I start right away with my presentation. So I hope you can see my screen now.
Yes, it's clear.
Good. Okay, so my talk is Heavy Quark Decays, Gate to New Physics is a question mark. And I understand that you all are particle physicists, but most of you will not work in theoretical flavor physics. So my talk will be somewhat introductory on the topic of flavor physics. And then I will dive into current trends of research. So the fundamental question of physics are: what are the smallest building blocks of matter? Which forces act between them? And how did the university begin? And the first two talks are the core questions of elementary particle physics. The third one is cosmology and astrophysics. And as you all know, since the last 3 decades, these fields tend to merge more and more. So the contents of this talk is I start with a standard model, remind you of the important ingredients for the stuff which I want to discuss in the remainder of the talk, and this involves the search for, includes the search for new physics. Then I describe what precision flavor physics has to do with this, and I discuss the famous flavor anomalies, and then I'll summarize. So standard model, we start with the building blocks of matter. These are the fermions. And these are quarks and leptons, spin 1/2 particles. And as you know, all these fermions, which we know, are grouped into 3 generations or 3 families. And the field, which I will discuss later, flavor physics, will discuss transitions between these different families of fermions. So the standard model has 3 gauge forces. And they involve gauge fields, the gauge fields of the hypercharge and of the weak interaction form the famous electroweak interaction, which is governed by the gauge group U1 times SU2. And the 3 gauge bosons, W plus, W minus, and the Z boson are massive because the electroweak symmetry is spontaneously broken. The third gauge force is SU3. It's related to the strong interaction, and the corresponding theory is the quantum chromodynamics. The very important ingredient of the standard model for having massive particles is the Higgs boson. It has spin 0. It's the only fundamental spin 0 particle which we know. It has been discovered 10 years ago at the LHC, and it gives rise to 2 new types of interactions. The first one is the Yukawa interaction, so the Higgs couples here to the fermions, and that is highly relevant for this talk. And the second interaction of the Higgs field is the Higgs self interaction, and that is of course highly important for breaking the electroweak symmetry. So we have a Higgs potential, and the minimum of this potential does not coincide with the symmetry point. So often people, if you look into the public media, they speak about a fifth force if something is postulated which does not fit in the standard model. But if we count correctly, we see already the standard model contains five interactions. Yeah, we have here the 3 gauge interactions, and here we have the Yukawa interaction of the Higgs and also the Higgs self interaction. So this is already 5. If you then count the gravity as the next one, which is not included in the standard model, you can say that we already know 6 different kinds of forces without saying anything wrong. So this term fifth force is related to the fact that people have these ones on the radar screen, but they do not have in mind that also the Higgs field is communicates the force between particles. Okay, so of course I use natural units. If you are a theorist, you are completely familiar with this. I put h bar equals c to 1. And these units were introduced long ago by Max Planck, who also set, of course, other constants to 1. And then he found out if we do this, all units which we have in nature are powers of the unit of mass. And then he fixed this mass to the Planck mass, which he derived from Newton's constant. And then he said this is the most natural way to define physical quantities. And if you look into his paper, you will find the phrase below, which is German, and I translated it to English because I find it quite entertaining. So he stated that his natural units necessarily keep their relevance for all times and also extraterrestrial and non-human cultures, and therefore can be denoted as natural units of measure. So I find this interesting. So I think everybody agrees if you meet a space alien and discuss physics with him or her, you will agree that natural units is the first thing you will agree on. However, these non-human cultures, I'm not so sure whether we really will discuss physics with our horse or dog or so. So I find this a bit too enthusiastic what he said at the time. Now I study exactly this promised Yukawa interaction, which I discussed 3 slides ago. So we have 3 generations, and we can label them as D1, D2, D3 if we mean the down type quarks, and U1, U2, U3 for up, down, and top. However, you see these fields get a prime, and that has a reason. So if I start with the fields which fit into the multiplets of our gauge group, so especially into SU2 doublet, I have these prime fields, and they do not coincide with the fields describing the particles which we meet in our experiments. So the reason is the following. So the Yukawa Lagrangian describing this interaction of the Higgs field with the fermion fields involves so I describe it here for the quarks. It holds similarly for leptons. So it contains quarks from all generations, and we label the generations here with J and K. And you see that this Yukawa coupling is a matrix in this space of 3 generations. So these are 3 by 3 matrices. And here you see the coupling to the Higgs field. And this Lagrangian has, as you see immediately, is much uglier than the gauge interaction. So the gauge principle is very powerful. Yeah? You have a very deeply rooted symmetry principle, and you see at the end of the day you have a single coupling, a similar number per interaction. And in this case, we have these matrices, these 3 by 3 matrices. So that sees there are many free parameters in the Yukawa sector. So if we write this Higgs field as a number plus h prime, then we do this for the purpose because this our Higgs potential develops the vacuum expectation value V. So and then we can split this constant term off, and then the fluctuation around the minimum are described by H prime. So what interests us is really the first term. If you plug it into the Yukawa Lagrangian, you see that you have two mass matrices, MD and MU, which you get by multiplying these 3 by 3 matrices with the WEF. So you have 3 by 3 mass matrices. And as you might, if you are an expert, you see immediately I normalize my vacuum expectation value to 174 GeV, which is the most convenient one if you do flavor physics. So if you would do electroweak precision physics, you would rather not include this factor of square root of 2 and work with 246. So don't be scared if you are puzzled if you miss certain factors of square root of 2 in this talk, which you are used to from other presentations. Okay, so to find the physical quark fields, so these are the ones which correspond to the particle which we see in experiment, we must diagonalize these mass matrices by unitary rotations of our vectors of quark fields, and there are different rotations for the left and the right-handed fields. So I label them here. The chirality is in the label of the field. So which effect does this have? This unitary rotations diagonalizing these matrices drop out everywhere except for the coupling of the W bosons. So that's the point where unitary rotations are still present. And these unitary matrices V, which are some combinations of these unitary rotations of the 3 types of quark fields, are physical. So this is V, and V is the famous Kawibu-Kobayashi-Maskawa matrix, or also called the quark mixing matrix. So V is the only source of transition between quarks of different fermion generations. If V would be the unit matrix, the quarks of all 3 generations would be stable. So this is roughly the experimental situation, or the structure of this Kobayashi-Maskawa matrix. So instead of labeling them with numbers, we prefer to label them with the quarks in which couplings of the W boson, these elements occur. And you see that this matrix has a very particular pattern. So it's pretty close to the unit matrix. So the diagonal elements are close to 1. And the elements in the far out in these corners are the smallest in magnitude. You also see that these elements are complex. So I set some tiny complex phases to 0 in this approximation, and these complex, the imaginary parts here will contribute, for example, to CP asymmetries, so charge parity asymmetries. So to summarize, the Yukawa interaction is the only source of transition between quarks of different flavor, so the only source of flavor violation in the standard model. So Yukawa interaction is the origin of this, but the phenomenology of flavor violation is in the W couplings, which inherits it from the Yukawa sector after we rotate fields from a symmetry basis to a physical basis, a basis of mass eigenstates. So the strength in flavor violation is encoded in V. So the smaller these elements VUB, the less likely is the transition of the field. And this gives an example for the U bar B couplings, so the B to U transitions. So flavor is just a different word of fermion species, and flavor physics studies the transition between fermions of these different generations. So now the standard model. In the standard model, flavor physics is therefore the physics of the Yukawa sector, and that's how the field was seen for many decades. If we do flavor physics, we study the Yukawa sector. And nowadays, the viewpoint is a bit different. If we study flavor physics, we study the standard model as a whole. We look for new physics, so effects of physics beyond the standard model. And this new physics need not be related to a modification of the Yukawa sector, but it can comprise really different sectors, and they they go into the observables of flavor physics through loop corrections or to loop contributions. So the Yukawa sector has 10 parameters for quarks and also several parameters for the leptons. So we have 6 quark masses. And by measuring or by knowing quark masses, we can immediately find the Yukawa coupling. So their masses over VEF. And we have 4 parameters in this unitary CKM matrix B, 3 angles and 1 phase. And this phase is a physical phase. So that means there's only one fundamental phase. And that means that you can pick, for example, gamma as the phase you quote as a fundamental phase, and then you can calculate the other ones in terms of gamma and the magnitudes of these other elements. So this relation means we knew the Higgs couplings well before the Higgs was discovered. So that is the role of flavor physics in the standard model. And I go to my next topic, the search for new physics. And I start with 2 cornerstones of quantum field theory. Forces are mediated by the exchange of particles, which are described by fields. So a particle of mass m mediates the force ranging over the distance 1 over m. So what does that mean? If we want to discover or if we want to understand this force, we want to discover the particle, and that would lead us to the conclusion that we should build colliders with higher energy to produce new heavy particles. A particle with mass m contributes through quantum effects to physical processes at energies well below m. So this means the particle contributes as a virtual particle. So this is a mandatory consequence of all these of the principles which go into quantum field theory. And if you want to study new physics exploiting the second feature, you are guided to build high precision experiments which compare predictions of the standard model with experiment, and then you try to find deviations. So these are the 2 routes here. And what guides us in the second approach is the so-called decoupling theorem. And that means that implies that we can organize particle physics in terms of hierarchical energy scales. And this decoupling theorem was originally found by Appelquist and Carazzone in the context of heavy particles in the strong interaction. So what does it say? So if a gauge theory is valid at some energy scale m1, and this theory is embedded into larger theory with new particles of mass m2, which is much larger than m1, the effects on observable probe at the scale m1 are suppressed by powers of m1 over m2. So if you send m2 to infinity, it means the effects vanish of the new physics. So the decoupling theorem has a blessing and a curse. So the blessing is it helped us to structure our field of physics. So we could formulate atomic physics without understanding nuclear physics, because any effects would be suppressed by these towers of 10 eV over 100 MeV. And we could formulate the standard model without understanding, say, quantum gravity, which is governed by a much higher scale here, 10 to the 19th GeV. So if the decoupling theorem wouldn't hold, the atomic, nuclear, and particle physicists would all be the same, so we would all work in the same field, and probably there would not be much funding in physics because the whole field would look like collecting butterflies and not in terms of understanding nature in a well-organized mathematical way. So that's the blessing of the decoupling theorem, and it's shown here in this chart. Now the curse. So that means if you want to find new laws of physics beyond the standard model, we must either build colliders which probes this new energy scale directly, or if we go to precision experiments, we must reach very high statistics to reach the precision of ESM squared over E2 squared. And here I already put in that effects which we can probe in quark flavor physics are suppressed by 2 powers of this scale. So in fact, most of the new physics enters at this level. The only level which is the only new physics which enters linearly in the ratio of the 2 scales is related to neutrino masses, and this is not relevant for this talk. Good. So physics beyond the standard model. Sometimes if you meet colleagues, they said, why bother to do this? The standard model describes everything perfectly anyway, and you will never find anything which is new. And indeed, the standard model is fantastically successful. It describes the results of terrestrial experiments between the mass scales of 4 microelectron volt, which is the energy scale of the lamp shift, and 4 tera electron volts. So is it the most successful theory of science? In my opinion, yes, but it is not perfect. It's not complete. So it fails in cosmology. We don't have dark matter particles. That violates the Sakharov criteria. So that means we cannot explain why we have a surplus of matter over antimatter, and there's also no explanation of dark energy. So this standard model, if it were the whole story, there would not only be no dark matter in the universe, but also no matter at all. So we would have a universe of radiation. It has also shortcomings, so it does not explain very fundamental things. So, for example, why the electron charge is 3 times the charge of the down quark. It does not answer us what the nature of neutrino fields are, neutrinos, Dirac-Majorana particles. It has 26 or 28 free parameters, depending again on the nature of the neutrino fields, whether it's 26 or 28. It does not predict these masses because we see their couplings times the Higgs wave, and these couplings are free parameters, and there's no gravity. Good. So now what can flavor physics tell us about physics beyond the standard model? And the prime strategy for precision physics is we identify observables for which the standard model contribution is parametrically suppressed. So that is the way to outsmart the decoupling theory. So you know, we have this suppression by the ratio of the 2 scales, so the scales of the standard model and the scale of new physics squared. And in order to outsmart it, we look for processes in which the standard model contribution is already suppressed. So if something is suppressed in the standard model, you are more prone to see the effects of new physics. And that guides you to flavor-changing neutral current processes. So in the standard model, these flavor-changing neutral current processes are loop-suppressed. And they're loop-suppressed quantum effects. So what is flavor-changing neutral current? It means that you have a transition from one quark to another one. So here, say, from anti-B to an anti-S quark. And they belong to different generations. So that's why it's flavor-changing, but they have the same electric charge. So the transition is neutral. And that only works if the W boson appears in a loop. And that gives you this suppression by this quantum loop. And here on the internal line, you can, for example, have a top quark, and that means that you already probe high scales in a B decay, the scale of the top quark, and indeed that this feature was important to get some estimate of the mass of the top quark well ahead before the top was discovered. So this is called the gluon penguin diagram. And this is the Z-penguin diagram. So here you have the Z boson. So the gluon can couple to any quarks. The Z boson can even couple to both quarks and leptons. So why are FCNCs so interesting? So FCNCs are super small, but not so small that you wouldn't be able to measure them. So they are well measured. However, they are small because several suppression factors pile up. The first one is they proceed through electroweak loops. There are no FCNC tree graphs. They are further suppressed by small CKM elements. So the CKM matrix is so hierarchical, and if you go from B to top, and back from top to S, you have VTBs of order 1, but VTS is already 0.04, so you have a small number for guaranteed in your loop. So the suppression of loops with charm on the internal line or with down-type quarks are further suppressed by the difference of light quark masses squared, or of the difference of the square of light quark masses divided by the W boson mass squared. And this is called the GIM, or Glacial-Liouville-Mariani effect. So this is highly relevant for kaon physics and also for the physics of charm, charm decays. So there's further, in some cases, an helicity suppression in radiative decays or leptonic decays. So like B to S gamma is the radiative decay. Leptonic would be a B meson going to a muon pair. And that has roots in the fact that FCNCs involve only left-handed fields because the right-handed particles do not couple to the W boson. So any helicity flip brings extra suppression factors. Good, so generic models of new physics typically have new sources of unsuppressed FCNC transitions. So that's important. So suppose all this suppression mechanism would be the consequence of a fundamental symmetry that would equally hold in a model of new physics, and you would not gain anything because you compare suppressed with suppressed amplitudes, but that's not the case. So if you have new physics, FCNCs can be unsuppressed, and you basically encounter this in most of the models. So it's sometimes more seen as a nuisance than as a blessing, but for us flavor physicists is of course a good feature. So add extra Higgses. If you don't put any symmetries in it, you have immediately Higgs mediation at tree-level, Higgs mediated FCNCs. If you add in supersymmetry, so quarks and gluinos, you can have flavor violation in these couplings and of quarks, quark and gluinos. So, and has nothing to do with CKM, so you do not expect a suppression here. You have vector like quarks. This is something, some way to add fermions which are very heavy. Then you can have FCNC couplings to some extra Z prime boson. That's a possibility. And if you have right-handed gauge bosons, you can overcome the helicity suppression. So these are things which I will discuss. So we do not produce free quarks in an experiment. We have hadrons, so bound states of quarks and antiquarks or of quarks. And the ones which are interesting to us are the mesons. And the mesons consist of an antiquark and a quark, and the naming scheme is shown here. So I will discuss these guys. So like charged kaon is anti-SU, charged D, and so on. Of course, talk a lot about B mesons. So these are the charged B mesons here, and the neutral ones are here, B bar D and B bar S. The neutral ones have an extra goodie. They form quantum mechanical two-state system. So that means if you produce a neutral B quark in time, it will oscillate in a quantum mechanical superposition of B and B bar. And this is a gold mine to study, for example, CP violation. So what are the new physics discoveries of the past with FCNC processes? So in 1964, Dutch parity symmetry violation was seen in K2 pi pi decays. And that came what people see. So with the knowledge of today, we knew that comes from this box diagram. So these are W's here, S going in, anti-S going out. So strangeness changes by 2 units. This is KK bar mixing. And at that time, from this measurement, you can infer, or you see an effect of the top quark mass. And the top quark mass is 350 times larger than the mass of the kaon. So that means that proved already with FCNC processes you probe have very heavy mass scales. Of course, at that time, nobody had any clue about the top quark. So the charm quark was postulated after seeing the suppression of K2 mu mu and of KK bar mixing. And this was in 1972 or something around that time. And the heaviness of the top quark was confirmed after BD bar mixing was found by the Argus experiment at DESY in 1987. And direct CP violation in K2 pi pi was discovered in 1999 by two successive experiments at CERN. So the first one was so-called indirect CP violation coming from this box, and this comes from the decay amplitude. So next, why is B physics so especially interesting? So the point is the B quark cannot obviously decay to a top, so it must decay to up or charm. And that means you already have a suppression in the decay amplitude. And if you calculate the total rate, you get it squared, the suppression factor. So it will most likely go to a charm, and VCB squared is 2 times 10 to minus 3 roughly. And that means the total decay rate is small. That means the lifetime is long. And that is important for experiments. So you have a pretty long-lived particle of 1.5 picosecond lifetime. Furthermore, what you measure in experiment are branching ratios, so partial decay widths decayed by the total decay width. And they are enhanced because the total decay rate is so small. Compare this with the top quark. So the top quark has a depressingly large width. So in top decays, you by far do not have this sensitivity. So this motivates B physics. And this is the famous, these are the famous asymmetric B factories operating at the beginning of the century. One is the Belle experiment at the PAC II collider, and the other one is the Belle experiment at super KEC-B. In Tsukuba, we are now with a successor experiment called Belle II, which runs since 2018, but it's currently shut for upgrades. The other important experiment is LHCb at CERN, and that is their B mesons or any B-flavored hadrons are produced in proton-proton collisions. And so here's the beams. And it looks like a fixed target experiment, but it is not. It's just a forward detector, because most of these B-flavored hadrons are produced with small transverse momentum. So there also, you can produce all kinds of B-flavored hadrons, including the baryon. So the lambda B baryon is a BUD bound state. So what have we already seen by studying flavor physics? So in recent years, there are several discrepancies between measurements and standard model predictions seen, and they are denoted flavor anomalies. So the first one is a set of observables in B2S mu mu. And now you see a special feature of flavor physics in general and B physics in particular. What we want to study is new physics, which is has to do with heavy particles, and these new interactions coupled to quarks, of course, and not to the hadrons as a whole. So that means if you have new physics going into this decay mode, it will affect many different hadronic decay modes. So you can have the S can sit in a K or in a K star, so you can see it in B2K or B2K star. You can also use the B sub S meson where it goes to phi, and you can see use the lambda B baryon and it goes to a lambda and so on. And this redundancy gives you a lot of the possibility of many experimental checks. So if it's new physics, you should see it in many such decays, not just in one. The next one is the anomalous magnetic moment of the muon. And this is somehow hijacked by the flavor community by noticing that this is, of course, not a flavor changing process, but this G-2 of the muon is proportional to the Yukawa coupling, and Yukawa sector is the home turf of flavor physics. So here we have a deviation from the standard model prediction. If you predict it in the standard way, which involves experimental data from E plus E minus collisions to tackle certain contributions entering G-2. The third one is B2C tau nu, so bottom to charm, tau lepton and the neutrino, and the enhancement of the, we see here an enhancement of the ratio of branching ratios if we normalize them to the corresponding decay with a light lepton L, which is E or mu. And that started with D and D star here, these two decay modes, but in the meantime, we have two more decay modes, which also probe B2C tau nu. And that, if you just look at these two alone, this is 3.2 sigma off. Yeah, and at least in the beginning, we saw some inconsistency between experiments which contribute here. So start with the first one. These are things which we can study. We study several observables, but I start with these ones. So RK star is the ratio of B2K star mu over the corresponding one with electrons. RK is analogously defined. And you can do the same thing with the BS, and so far we have only information on the dependence of Q squared of this quantity, but no R ratio so far. So this Q squared is the invariant mass of the lepton pair, so you measure these things and you bin it in the regions of Q squared. So the error of the standard model prediction is essentially 0 here, because that should be very close to 1. And in B2K star mu, we have more information also from angular distribution of the decay product. Here the theory predictions and the estimates of the uncertainties is more difficult. They have funny names. So one famous one which deviates from the standard model has this name P5 prime. The definition is quite complicated in terms of kinematic variables. So you can monitor the progress of the field, or when you go to this web page of Patrick Koppenborg, who works in the LHCb experiment, and this is the status of flavor anomalies. This is a pool in standard deviations, and I mentioned RK and RK star, and you see there's a pool, but the pool by itself, so none of this observable by itself is above 4 sigma. So this claim that there could be new physics is based on a global analysis of many observables. Here you see this P5 prime, and here the plot is a bit misleading. So because the quantity is defined with a certain sign, all of these deviations are consistent in the sense that we see too few muons. We see less muons than we expect in the standard model. And because of this feature that B-physics measurements are highly redundant, which is a good thing, so different observables depend on the same theoretical quantities, we do need combined analysis and likelihood ratio test between the best fit point and standard model point for the theoretical parameters in order to determine the overall significance of this. Okay, so if you combine anything, you find a spectacularly discrepancy, which is far above 5 sigma, so it's closer to 6 sigma. Of course, there's a little problem. Suppose you have a correlated experimental effect that you somehow screw something up with muon detection, it would affect all observables alike. So why they are redundant, they are not completely independent of each other. So in theory, we calculate Feynman diagrams, and the results we put into an effective Hamiltonian. You see familiar things here like Fermi constant, the CKM elements, and then we have something here which describes the interaction mediated by such diagrams in terms of a point-like interaction. So that's something you know from Fermi's theory of beta decay. So you contract this loop to a point, and this point-like interaction is described by these operators O9 and O10 in my example here with the Z boson, and they come with generalized coupling constant, which we call Wilson coefficients. So these are numbers. They're real in the standard model, real numbers in the standard model, and then we have these effective interactions, and we will discuss about O9 and O10, and these differ only in the nature of the coupling to the leptons. This can be a vector-like or an axial vector-like coupling, that is O10. So now you see that that I included here the possibility that I couple two leptons of different kind. In the standard model, this must be the same. So that must be both muons or both electrons. That means we would only have O9 mu mu, O9 EE, and so on. And also the couplings would be exactly the same. Good. So these are these mentioned operators. And in the standard model, as I said, we have only these coefficients, they are all the same. And the ones where the two flavor indices are different are 0 in the standard model. So this is a famous angular distribution, P5 prime. And that was the one how the whole field started. It started in 2013, roughly, where the first statistically significant hint was seen. Yeah. And it is this one. So you measure this Q squared. There are gray bands which you cannot access because some resonances are in the way. And here you see the prediction from the standard model is orange, and the black crosses are the data. So these are the lepton flavor universality violating ratios, RK star and RK, which came up later afterwards, and they somehow moved some theorists from the camps of skeptics into the camps of believers. And this feature, which I mentioned here, that all these couplings are the same, comes under the name of lepton flavor universality. It's a cornerstone of the weak interaction, and there should be equal to 1. And this test is very powerful because of the small theoretical uncertainties. So this is the experimental situation, and I stole this slide from Johannes Albrecht, who is in the LHCb experiment, and you see roughly 2.5%, 2.5 sigma deviation in RK star. It's smaller than 1, and for RK, this is for the charged mode, it's even 3.1 deviation. And the trend is the same in all these other modes, so we see this deficit of muons. So this is a global fit from this reference of this year, and you see these fit to the two coefficients C9 and C10. Mu, so it's coupling muon to muon. So again, I show you the operators again here, and this is the plot, and you see that not only LHCb contributes, but also other experiments. So for example, CMS and Atlas, and you see also LHCb is the driver of the measurement. So the standard model point would be here, 0, 0. So this is only the new physics contribution. The standard model contribution is subtracted in this plot. So the standard model sits at 0, 0. And you see the preferred region has deviates from this point. That it's here. So the combined significance of the anomaly is too large for statistical fluctuations. So that doesn't mean it's correct, because there can also be issues with the experiment, like you have some systematics which you estimated in the wrong way. But as a theorist, it's not my role to have an opinion on the experiment. So the standard argument is the efficiencies of E and mu could be incorrectly estimated, and there's a little control channel here. You look at the decay into J psi, so the J psi is a CC bar resonance, which equally with equal strength goes to a pair of electron and muons, and that is also measured. So you know this from experiment, and because you measure this double ratio, the efficiencies for the electron and muon detection drop out. So that gives you a confidence that you understand your detector when it comes to detection of muons and electrons, which by the way look very, very different in the LHCb experiment. So to first approximation, this efficiency cancels. However, the interesting bins for the anomalies is here and here. These are the two bins which deviate from standard model. And of course, for the resonances, the Q squared is larger. So that means there are some effects. So there's this famous saying of Sherlock Holmes: every extraordinary claims require extraordinary evidence. And currently LHCb is reanalyzing all the old data with the new team, and as I understand, also a new method, and stay in tune because they are scheduled to present the result of the reanalysis close to December 20 on a Tuesday in the usual LHC particle colloquium, particle seminar. So what could be new physics explanations? So a very popular one involves so-called leptoquarks. So these are neither leptons nor quarks. These are bosons which couple a quark to a lepton. So these are some examples. And these are examples, let's go to the very right diagram where you have BS and then the leptons here. So, and they appear, in principle, at least the species of leptoquark could explain all anomalies, though in general you need different leptoquarks for different of these modes. There are some exceptions to this statement, but that's a general picture, and they appear in any theories where leptons are united with quarks. There could also be a Z prime boson, so this explanation is under pressure more and more, and that might also help with G-2, but not with B2C tau nu. So this is a situation as we knew it, say, at the beginning of the year in B2C tau nu. So that's again studied through such ratios, which we understand fairly well in the standard model. You see it with the error bar of the standard model prediction here, which is tiny compared to the experimental error, and also with respect to the deviation between the standard model and the best fit point. And the nice thing here is that many experiments contributed, starting from Babar 10 years ago. And it continues until today. And you see on the next slide a measurement from this year. And you see that all these experiments see consistently something higher, with maybe with the exception of yeah, even here the central point is above the standard model. So some experiment only measure RD star, they give this band, and many measure both in a correlated way. So this is the situation in 2022. We have a first measurement by LHCb, which goes beyond R of D star. So it includes now R of D. So the first time R of D is also measured at LHCb. And there was a surprise. So the surprise is here. That is the 2022 ellipse. And it suddenly supports this Babar measurement. So if you go back at the beginning of the year, you said, hey, come on, these measurements are not in good agreement. They're also not in completely bad agreement, but they deviate more than you would expect by statistical fluctuations. And you see Babar 12 lost lots of its supporters because it's a kind of an outlier. So this year, LHCb suddenly is nicely consistent with the old Babar 12 measurement, and now if you look at the complete picture, you suddenly see that you have quite a good consistency between all these measurements. So now it fits better what you expect from statistics. And you also see that the large RD is somehow vindicated or corroborated by the data, but the RD star is slightly coming down. So we move a bit from to the right and down. So this is the situation as reported on the heavy flavor averaging group's webpage, including the new data of the year. So this is the experimental situation. And below there's a standard model prediction, which HFluff takes by averaging several theory predictions. These are these numbers, so they go here. And the significance is as large or as small as it was before. However, the picture changed in the way I just described it. So the point is, the nice thing is several experiments contribute, but maybe the effect is a bit too large because after all this is a tree-level decay. So we could be worried about this one. This is, by the way, the picture I took from this reference. It was the postdoc in my group here, and it shows you how the new combined average changed from the situation last year with this LHCb measurement. So you go from the dashed lines, here the red dashed line, to the solid lines, and you see how the ellipse moved here. Again, we can have several new physics explanations, and the classic interpretation of anything which would to be discovered in this mode was already from 1992 when it was seen by Jatkowski and George Hu that there could be a charged Higgs boson which interferes with the standard model W exchange. So the charged Higgs boson can have large couplings to both B and tau. So the two Higgs-W models studied at that time are not the ones which describes today's data, but we have to find these couplings. So the leptoquarks are again in the game, and they have names like S1, S2, U2. These labels have to do with the quantum numbers. The quantum numbers are mentioned here. Singlet is 1, doublet is 2, and so on. And they have different electric charge, and they could all contribute. This is a vector one. This is currently the darling of theory because it could in principle explain all anomalies at the same time. The good news about B2C tau nu is you can make it a black box. So the black box can be any of those, and you fit to the coefficients of effective operators. So there are few enough that you can do fit to coefficients, you get the best fit point, and only afterwards you think about which new physics this could be. Several people have done this, and I refer here to an old work of my group from 2019 and the recent update from 2 weeks ago. So in order to find to fit this coefficient, you take RD and RD star, but you can also use the tau polarization in the D star decay, as the D to D star decay, with a Belle measurement and the fraction of longitudinally polarized D star mesons from Belle 2018. And if you do this, you find these results. And what we studied are all scenarios for these coefficients which correspond to a single particle exchange. So in some sense, we do put in some information or some assumption on the ultraviolet physics here. So if this is an S1 leptoquark, we have a real vector CVL coefficient, or which we can take real for this analysis, and the scalar coefficient is -4 times the tensor coefficient. So tensor operator is this one with the sigma mu nu here. Similarly for other scenarios, and every scenarios can fit the data, but they make different predictions for this poorly measured quantity. So we predicted them and said measure them more precisely, this FLD star, for example, and you can distinguish. Also, this BC to tau nu is a player in this field. So in the case of the charged Higgs scenario, you either find a too large or a suspiciously large branching fraction of BC to tau nu. So this hasn't been measured yet. However, we know the lifetime. And at some point, if a partial decay rate becomes larger than the inverse of the measured lifetime, you already know this cannot be true. So the lifetime by itself gives some bound on the rate of BC to tau nu. And so this calculated branching fraction should not be bigger than 1. That's what it means. And in the case of charged Higgs, you see this interesting pattern. You either see a very big branching fraction, or RD star will come down. And indeed, it was a 2019 prediction, and it's because RD star came a bit down, this charged Higgs explanation becomes more viable. In fact, people had ruled it out already, but it's still alive. That is one result of that paper, and it's corroborated by today's data. So in the leptoquark cases, you also see a particular pattern. So this FLD star will be more standard model-like, so that would distinguish between those. And S2 is similar to the charged Higgs one, except for the FLD star case. It's also testable in colliders. Good. So what is new? So in the meantime, this was measured, the baryonic decay. And there's one point which we found in 2019, and that was that there's a correlation between RD star, and R lambda C. So we called it a sum rule. So you measure 2 and you can calculate the third one. So that is surprising because it holds in any scenario of new physics. So no matter what all these new physics coefficients in, you have this relation with a small reminder, which is less than 5% here in this equation, which does depend on the new physics model. So in general, you measure 2, you predict the third, and that was exactly what he did in 2019. So why is this possible? So there is such a relation that roots into the so-called heavy quark symmetries of QCD, and you can somehow optimize these coefficients in a way that so this relation holds exactly if the B quark would be infinitely heavy, and you can refine this coefficient in a way that you capture the dominant 1/MB corrections to this relation. And in the end, you find something like this, which you can probe in experiment. So that's what we predicted. Measure it, and you will find this number. So you see the small error here. Now, in 2022, the LHCb did measure it, and you see this does not fit at all. So this is away by well, maybe 2.5 sigma or so. So it's not completely disturbing, but you also see there's a significant tension. So that gives us a very simple prediction. With future data and smaller error bars, either this will go up or these guys will go down. Yeah, that's it. Very easy. So 2022 updates also include this one. So this was known in 2018, the RJ psi, but there was no reliable theory prediction. So in the meantime, this has changed. The lattice colleagues did a very good work, and this is predicted with a small error bar. And you see this is also bigger than expected, but the error bar is super sizable. So improvement on this is highly warranted. So this is R lambda B, and again, that is something you can compare it also directly with the standard model, and now you see it's smaller. Everything else was above, and this is one outlier where we see a deficit. So these are 2 updates. One I already showed you a plot from, and the other one is from last week, which includes also me as the co-author. So this is the update of the sum rule, because the data changed. Also, these numbers changed a little bit. The prediction is amazingly stable. So that was the old prediction, it's the new one, and it's basically identical. So the sum rule assumes that new physics only affects the tau mode. So the one thing we could think about, maybe all these measurements are perfectly fine. And the reason is that in reality, we also have new physics in the light modes. If that would be the case, the sum rule would not hold. The sum rule assumes the new physics is only in the tau, in the decay into tau. So then we allowed for a fit where we permitted arbitrary new physics in all these coefficients. So even we went beyond these 4 scenarios. We took them all coefficient arbitrary for the tau case, but also arbitrary for the light leptons, except that we made no difference between electron and muons, because that would not improve the fit. And nothing changed. The tension is still there. So this does not help at all. The new physics effects in the light modes, if they exist at all, they are too small to have a relevant impact on this R ratio. Good. So that concludes my talk. So you see the several goodies in this field of BSM flavor physics. So the first thing is, first point of my summary is we see that that's a general statement is we see that flavor physics poses virtual effects of heavy particles masses far above the reach of high PT experiments. Predictions of BSM theories for B physics observables are highly correlated because many quantities depend on few coefficients encoding the BSM effects. And these coefficients are the ones we can calculate reliably. And for the matrix elements, we often need sophisticated non-perturbative methods, and we take them from our colleagues who work in lattice gauge theory. So this is an intrinsic redundancy of B physics that if you have new physics, you have to see it in different hadronic decay modes, which have different experimental advantages and disadvantages. So this redundancy really stabilizes the quality of predictions or of conclusions derived from flavor physics. So combining all B2S mu data reveals a tension with a significance somewhere between 4.5 and 7.3 sigma, and that depends on how conservative you are on hadronic uncertainties, and also whether you use Bayesian or frequentist statistics. The little Achilles heel is that there's a correlated experimental issue with muon versus electron detection efficiency, but there will be an update soon from LHCb. So we can, if B2S mu is true, this new physics, whatever goes there in the virtual, as a virtual particle, it must be below roughly 40 TeV. So suppose it's a leptoquark, but it's also this mass limit holds for any model of new physics. And this means that precision physics can give us guidance to design a future collider. So if this is true, you get a guaranteed discovery if you build a sufficiently powerful collider. So leptoquarks can also help T-2 and in B2C tau nu. And the new LHCb measurement of R lambda C points to an inconsistent measurement of at least one of these 3 ratios. So you see the redundancy at work here. It helps us to distinguish between BSM physics and experimental issues in this case. So the redundancy of B physics indeed helps us to disentangle BSM physics from mistakes, which can also be in some theoretical mistakes, need not be experimental mistakes. So this B2C tau nu is a 3-level decay, but B2S mu is the penguin decay. So maybe the penguin gives us the wake-up call for new physics. Good. That concludes my talk. Thank you very much for your attention.
Yeah, thank you very much for this very nice talk and very helpful for students. So is there any question or comment from our audience? Yeah, if you have any question or comment, you can directly ask. You're in your mic.
I cannot see the chat. If you put it in the chat, you should read it to me because I'm sharing the screen.
Okay, I will let you know if there's some question in the chat.
Sorry, this is Peter Atheron here. I'm sharing an office with Cheating, so I didn't want to unmute on my own machine. But yeah, so this, how do you put it? This issue with RD star and lambda C, yeah, it's suggestive that there really is something more going on here, and we don't really know it's new physics. But if that's the case, do you have some feeling for what might be wrong, what could be wrong with the colliders if there's a problem, and this isn't just a statistical thing that will go away and we really return to new physics?
Yeah, so so if I look at the best fit point, if I fit all of them and make the best fit point, the best fit already tells me a tension, and we see that it's around 2 sigma. If we take R lambda C as published, but it reduces to 1.5 sigma if one changes. So what they measure at LHCb is always a ratio of ratios, if you wish, with this lambda C. So if one changes some input that was pointed out by the group in Bonn by Bernlochner, it would increase this R lambda C a little bit, and the tension would go down from 2 to 1.5 sigma. This is not really disturbing. So with more statistics, maybe the central values will move of this R lambda C. So I go back to the measurement here. So this is still an error of which is I don't know, more than 30. No, this is much more. It's very large, and that means that I have a kind of a bias, but that's a theory bias. I think that this number is more likely to change than RD and RD star, simply because for RD and RD star there is a 10-year experience with measuring it. It goes back to Babar, and this RD and RD star is in the end supported by Babar, by Belle, by LHCb, and Belle uses even 2 different tag methods. So these are 2 completely different data sets. So that means there's much more support than for R lambda B. So eventually the experience with this kind of measurement is not that long lasting. It's less than a year that this is out, right? So that is, but that is just a feeling from an incompetent theorist. So an experimental colleague should better comment on this feature.
I see. But if it was the other way around, then it weakens the evidence for BSM physics from the flavor sector.
Yes,
right?
exactly. So if R lambda C is confirmed, then we get this. We can turn things around. So suppose the left-hand side is 1. That gives you a correlation. So if one is above standard model, the other must be below, and vice versa. So that is implied by this. You also see that RD star has a bigger weight here. So if this goes to standard model, it makes it makes it easier to fulfill the sum rule. So RD, and in some sense, it's exactly what was the trend in previous measurements. So I go back to this slide. You see both are above here, and then because of LHCb, this ellipse moved to the right and down. So RD star indeed moves downwards, and RD, however, moves upwards. So suppose lambda C is completely correct, then this ellipse must in the end lie on a line which goes to the standard model point, but it should be in a way that if one is off on the negative side, the other must be on the positive side from RD and RD star. So everything is out here. The nice thing, but in my opinion, the nice thing is that the chart takes explanation, which is the vanilla explanation of this. That is something people predicted. The leptoquark solutions are post-predictions. So the only prediction was the charge 6 thing, and that people said in 2017 or so, well, that's basically ruled out, forget about it. It's back in the game. So the charge fix is not ruled out at all. However, also my postdoc, Iguru, wrote a paper that if this is a solution, you should find it at the LHC. So he gave a clear program which searches at LHC will either lead to a successful discovery of the charge fix or will indeed rule out this explanation. So that makes it interesting. So we will in a foreseeable time frame, we will know this. Charge fix is it, or charge fix does not explain it because LHC does not find it. So Atlas and CMS will not find it.
I also had a question actually about the vector leptoquark solution, which is just that is there a UV completion that still works? So
yeah, for the you're speaking about okay, sorry, it's B2C Tonio, the vector lab, this one, yeah.
Yep.
I think so. First of all, you cannot simply add a spin 1 boson to the standard model. You need some Higgses, for example, which give it a mass. Otherwise, the model would not be renormalizable. And people worked on this. So I give you some examples. So one example is you take SU4 model, so party salam. So you unite leptons with quarks, but then you triplicate it. You have 3 copies of this SU4 for 3 generations. That's studied in Zurich by the group of Gino Isidori. Another possibility is you take leptoquark model and sorry, a party salam model and put it into extra dimensions, but that would not explain B2C Tonio. It only works for B2S mu mu and G-2. Okay, so you want one which works also for B2C Tonio. Okay, so I gave you one example. Otherwise, I'm not, I don't know, but I'm not an expert on U1.
Yeah, one example is enough if it turns out to be true. Okay, thanks.
Thank you. Okay, I found there's 2 questions in chat from our audience, Li Xinqiang. So let me read these 2 questions for you. The first one is, how about the constraints from tau and D star polarization fractions? And the second question is, if there are any key observations to distinguish among different new physics explanations.
Yeah, so so the situation with the measurements is unchanged since 2019. And that means what I wrote here, which was from our 2019 paper, still holds. Yeah. So what mattered to us was, let me check. It was okay. This measurement is useless, obviously, 2017. So it has no impact on the fit. However, FLD star did have a impact on the fit, and it's on the high side. So it's 1.5 sigma above the standard model prediction. So nothing to worry about. However, it does impact the fit. And the funny thing was that FLD star does prefer the charge fix. So for the charge fix, we could reduce this, could perfectly explain FLD star, while in the leptoquark cases, FLD star stayed standard model-like. So that answers this question about the future. If we measure this more precisely, we have a discriminator between two explanations. S2 was similar to charge fix, so that means S2 is more difficult to distinguish from H+. And but here maybe collider physics will help. So FL of D star makes already a difference, but we also made predictions for the tau polarization asymmetry. So if the Belle II will measure this more precisely, you will also see that these scenarios are different. And in fact, in this old paper from 2019, we make plots correlating always 2 out of these several observables, and you see you can distinguish at some point, you can distinguish all scenarios. Does this answer the question?
Yeah, I think so. So is there any other further question or? Okay, he writes, thanks a lot, thank, yes. Any
Yeah,
further questions? Yeah, if not, then I have a question. So in your summary, you show, for example, for the using leptoquark model to explain the B to S mu plus mu minus, then the constraint for this match should be less than about 40 TeV. So in a future observation, is it possible to lower down this upper bound, for example, less than 10 TeV or so?
Okay, so the 40 TeV bound comes from the okay, so I yeah, I showed here this. So if you look at so phi 1 and phi 3 are also leptoquarks, so it's a different notation. And we look, this is the most sensitive one. If we have this B to mu mu case, and the 40 TeV come from the following consideration. We have coupling constant 1, so maximal strength. And if it's maximal strength, you get, of course, the weakest bound on the mass. And that is how we find this 40.
I see.
So suppose you find a physics region where these couplings are smaller, then you can eventually strengthen the bound. So suppose now you consider a model where this is all loop induced, then you immediately are a factor of 10 smaller. So if you need a loop to explain the data, you have at most 40 eV for the extra particle, because the loop suppression is there as well. So this 40 TeV is really the most conservative one. And for there, in the moment you have precise data, you could try to constrain couplings and masses with different observables. For example, you could close this loop and add a photon, and maybe B2S gamma breaks this degeneracy. So that is a guess.
Thank you. So I have another question. In page 53 of your slide, so here you mentioned a sound rule for the B to C tau nu. 50, yeah, here. So I still confuse the physical meaning for the X. So in this sound rules, you show the X absolute value of X should be less than 0.05.
Yeah.
So what is this meaning for this X?
Yeah, okay. So so these predictions here for these 3 quantities, they depend on the coefficients of these 4 operators. So they are complicated functions of all these operators. So you have contributions which involve the operator, say the coefficient of OSR absolute value squared, and same for the others. And then you have a contribution which is an interference. So it's the real part of the product of the coefficient of this and this operator, and so on. So you have many terms, and it turns out that in the sum rule, most of these effects are captured in these 2 coefficients, and then you have a remainder. So you have like a coefficient which is, say, 2 times the real part of this operator times this operator. So now we know the coefficients of these operators are way smaller than the standard model one, because the deviations are subleading with respect to the standard model. So in some sense, the product of 2 coefficients is smaller. Is smaller than the interference of the coefficient with the standard model, for example. And this X is the long expression involving all the products of small coefficients. And now we do a global fit. So we let all these coefficients float in the region where they explain the data. And then we take the maximum, which we see. And the maximum is 0.05. That's how it comes. So the X is a function of this coefficient. And also this axis has been refined between 2019 and 2022. So if you go to the update, the X is slightly differently defined. And you go to this paper, and this X is even a bit smaller than the previous one. So that means this sum rule holds really excellently if you just throw this remainder term away.
I see. Yeah, thanks a lot for your explanation. So is there any further question or comment? So last chance. Okay, so if no, let's thank our speaker again.
Okay, thank you.
Yeah, thank you very much.